Okay, so nothing too new here. It's asking us to look at, to calculate the potential difference at a point P. Again, just kind of getting us to think. This would probably be one where I would ask you to get up the whiteboards. So go ahead, pause the video, try this on your own, okay? And then if you want, come back and you can watch my solution, or you can just skip ahead to see if I got the same answer as you. So to calculate the electrical potential at point P, the voltage, okay, at point P, what are our options here? Well, we're probably going to be using our quote unquote parallel plate equation, right? Never good to pigeonhole an equation into one use, but realistically, this is most of the time we're going to end up using this equation. Okay, that's where it's most applicable. Now, to determine the electric potential here at point P, okay, yeah, you could kind of just say that it's going to be, well, 1/3 the value, if you can kind of look at it that way. But let's also just try and do it justifying it with an equation. Remember, what is changing about the electric field strength as we move from, let's say, here to here, okay, or realistically here to here, or here to here? What is changing about the electric field strength? And if you said nothing, you're absolutely right, right? The electric field strength, it does not change between two parallel plates. The electric field is uniform, and the force is uniform because of that fact, and the acceleration of a charged particle between the two plates is also uniform because of that fact. So this is not changing. Okay, so let's just solve this because we're solving for the potential difference. The potential difference is equal to the electric field times the separation distance. Okay, now if we're at point P, right, the distance we are has changed, right? We're no longer at that full distance. We have gone through some potential difference. If you want to think of it this way, if I put some charge there, the amount of kinetic energy it would gain has changed, right? It would no longer get the same amount of kinetic energy if allowed to accelerate from that position to the negative plate as opposed to that position to the negative plate. So what has it changed by? Well, it's changed by a factor of 1/3. The separation distance is now only 1/3 of what it used to be, okay? So really what we're saying, let's call it the potential difference prime at point P, okay, is equal to the electric field at point P, which we know, how does that compare? It hasn't changed, it's uniform, times 1/3 the total distance, because this d here, we'll call it d prime, equals 1/3 d. Okay, so if this is the same, right, then how does that affect our voltage? Well, voltage prime is now saying we're taking, let's just say 1/3 times the electric field times the separation distance. Well, hang on, this is just the original voltage, right? Not the prime voltage, just the original voltage. So the potential difference prime is equal to 1/3 the original potential difference, which, what's the original potential difference? Well, it's from 0 volts to 400 volts. That's the reference points they chose. So 1/3 times 400 volts or joules per coulomb. And that gives you 133 volts or joules per coulomb. That is the voltage at P. Perhaps maybe I should have used a P subscript. How about that? Okay. Now, here is a new concept. So that really isn't something new, but here is something new. The idea of equipotential lines. Okay. And let's think about these. I'm going to first ask you a question, because they really do make a lot of sense when you just kind of stop for a second and think about it. Let's kind of draw them ourselves. I'm going to actually erase this just to give myself some room. Okay. So jot that down if you don't have it for answering this question. Okay. But to get in the idea of equipotential lines, I am going to start with a point. Okay, now that point, I did my best to make it about halfway across. Okay, so let's say that's 1/2 D. Okay, 1/2 of D. Ooh, that looks terrible. Okay, so at this point, what is the voltage? This point right here, what is the potential difference? It would be about 200 volts because it's about halfway across, right? So it would have about half the potential difference. The work per coulomb, the joules per coulomb you would have to do to move a charge to there is about half of the amount you would have to do to go from there all the way across. The same way if you were lifting something against the gravitational force, to lift it 50 meters, just making up a number, to lift it 50 meters is about half the amount of work you would have to do to lift it to 100 meters per kilogram if we're comparing to voltage, right? Remember, in a gravitational field, there isn't really an analogy to voltage, but if there was, it would be the joules per kilogram to lift, whereas voltage is the joules per coulomb to lift against an electric field. Okay. Now, what would be the potential difference here? Or here? Or here? Or here? Would it really change? Okay, and the answer, as you might have arrived at, is no, right? Think about this again. It always helps to go back to the analogy of the gravitational field. To lift something from here to here, does it take any more work if you walk 10 meters east? You're gonna have to turn your head sideways to picture it, but if you walk 10 meters to the right, let's say, and then lift at the same height, did you do any more work over here than you did over here? No, right? Did you do any more work per kilogram here to lift it to this height? No, so you didn't do any more work per coulomb in an electric field to lift it to those, to move it against the electric field there, okay? So that is the idea of an equipotential line, okay? So an equipotential line is a line in which where the potential difference is the same the whole way through. Okay, so the potential difference the whole way through at that point would be, if it is perfectly halfway, like I've tried to draw it, that's an equipotential line. That's the equipotential line where the voltage, wherever you are on that line, is 200 volts. Okay, so at our point P, there's an equipotential line. So at P, we worked out the voltage to be 133 volts. It would take 133 joules for every coulomb to move to that position from our 0 reference point. Now, what about at this point just above P? What about at this point just below P? Is it any different than at P? No, it's equal, right? So the potential is equal. The potential difference is equal at P. So that is an equipotential line. At all points on that line, the potential difference is 133 volts. Now you can imagine we could kind of sit here and do this all day, right? Any vertical line we draw through this electric field is going to be an equipotential line. Any point on that line is going to have the same potential difference. Okay, so we won't spend too much time. Let's just do what the question asks us. It says, draw in an equipotential line where V equals plus 100 volts. So I'm going to let you pause the video again. Try that on your own. Okay, if you don't have the notes in front of you, think about it. Where would it go? Okay, or you can draw your own diagram to do it, but do try it on your own. So now, to draw that equipotential line at 100 volts, I got to think, well, if this is 0, okay, this is 400. Well, 100 is about a quarter of the way there. I can also use the fact that this is 1/3 then, so a quarter, slightly smaller than a third. So the equipotential line at 100 volts, right, if I drew it straight enough, which I really didn't, but I should have, 100 volts. That would be that equipotential line. And that's the idea of equipotential lines. They're just lines at which the electric potential is the same at all points, okay? The voltage, that is to say, is the same at all points. You might be kind of thinking, well, this seems weird, right? Why vertical lines always? I want you to imagine, though, think about the equipotential lines for not parallel plates with a uniform electric field. Think about equipotential lines, and this is even a better analogy for gravity. Okay, let's make a charge. That's a positive charge. Okay, what would the equipotential lines look like there, where the electric field is not uniform, where the electric field drops off as 1 over r squared, according to, right? If you were to draw an equipotential line here, what exactly would it look like? Okay, pause the video, think about it, maybe even try drawing in your answer. But you can imagine that the potential difference, okay, so again, this equation is saying that the electric field is not uniform. It drops off as 1 over r squared. But at a certain point, though, right here, let's say, the potential difference is, let's call it x. What about there? Okay, what about there? What about there? What about there, there, there? How many joules per coulomb would I have to put in to move a charge from there to there, or there to there, or there to there? Well, it would be the same, right? I'm moving the same distance away from the source charge causing the field. And so my equipotential line for, whoa, if I could draw, my equipotential line for a source charge like this, as opposed to a uniform electric field between two plates, would actually be a circle, okay? And should be the same everywhere. Of course, I just can't draw, okay? That's an equipotential line. At any point on this line, the potential difference is the same. Think about gravitational field. This one is really a good analogy to gravitational fields, right? If I draw the, I guess the Earth is more blue than it is green, right? If I were to draw the Earth with us on it, okay, or land on it anyway, if I were to lift some object, right, on the North Pole, if I were to lift it some height to give it some potential energy, again, thinking in terms of joules per kilogram, even though we don't really have a version of that in the gravitational field like we do in the electric field, where it's voltage, potential difference, okay? Would it take any more work than to do it at the South Pole? Or any less work than to do it at the South Pole? Would it take any more work to do that at the equator? Right? Would it take any more work to do it at the equator on the other side of the Earth? And since the change of potential energy is going to be mgh, right, and h isn't changing no matter where you are on the surface, the answer is no. The amount of work you're going to have to put in per kilogram is always going to be the same. And so we could think of that as the equipotential line analog for the gravitational force, okay? But this is the idea of an equipotential line. Anywhere on that line, the potential difference is the same. Think about also the kinetic energy gained if a charge is released at any point on an equipotential line. So think about the kinetic energy gained. Let's go back to our gravitational one. If I drop an object at the North Pole, and it falls to here, think about the kinetic energy it will gain. Will it gain any more or less than if you drop it from here? Right? Will it gain any more or less than if you drop it from here, or any more or less if you drop it from here? The same goes for our equipotential lines, both for a source charge and for these parallel plates. If I put a charge at this point, or at this point, or at this point, or at this point, doesn't matter, they will all accelerate to the same kinetic energy in the end.
Okay, so on the next page, page 18, this is kind of, again, one where I would normally say, try this on your own, okay, see how it goes. So pause the video if you want, try out these questions here. But when you're done that, you can come back and watch my solution or just skip ahead to see my answer. Let's go ahead and look at these charged parallel plates, and we're going to try and find the equipotential lines where the potential difference is 200 volts. Okay, so there should be, it says lines, but let's think about it. Is there going to be more than one vertical line on here where the where the potential difference is positive 200 volts? And not really, right? There's kind of only going to be one vertical line. There's going to be many points, infinitely many points along that line, but there won't be more than one line itself. So let's take a look at the potential difference here. We've got from negative 500 to positive 700, right? So what's actually the total potential difference across these two plates? So the total would be, if it's going from negative 500 to 700, well, that means it goes from negative 500 to 0, right? And then it keeps going up to 700. So in total, we have a potential difference across these plates of 1200 volts or joules per coulomb, okay? Again, what does that mean? It means for every coulomb of charge, it would take 1200 joules to move it from from this point over to this point, okay? Or the other direction if you had a negative charge. Now let's think about then, where would 200 volts be? So what would the halfway point be? Well, it would be 600 volts away from here. Okay, so if I'm 600 volts away from negative 500, then I'm at positive 100. So the halfway point would be positive 100. So we'll go a little bit more over, about 100 worth, 1/12 over, and that should be the A point anyway, where the potential difference is 200 volts. Now remember, is it any different here? Would you have to do any less work per coulomb to move it from here to here versus here to here, or here to here, or here to here, right? And of course, the answer is no. The same way if you lifted something against the gravitational field, it doesn't matter what point on the other surface you're at. What matters is the height that you lifted. And so all the way down here, whoops, that's not very straight, but you get the point. Okay, that is an equipotential line at 200 volts. So the potential difference is the same along that entire line. Okay, now it asks us, part 2, to draw the electric field vectors in between the plates. So they kind of reminded you there, but even if they didn't, electric field is always a vector. Okay, so they used the word vector, they didn't have to. That was nice of them. So which way would the electric field be? We got to remember the definition of the direction of the electric field. It's always defined as the direction of force that a positive charge would feel. So if I'm a positive charge, which way am I going to be pushed in this field? Am I going to be pushed towards the positive plate or away from the positive plate? Okay, so if I'm a positive charge, like repel, I'm going to be pushed away from the positive charge, the positively charged plate. I'm also going to be pulled, you can think of, towards the negatively charged plate because opposites attract like repel. So those are the electric field lines. Okay, we would draw more based on the strength of this electric field, but since we don't have the distance, we can't even really say for sure what magnitude the electric field has here. Okay, the force vector on a fluorine ion, and this is where your chemistry background might get you in trouble a bit, okay? In physics, when we talk about an ion, okay, if something is getting ionized, we almost always mean that it has had electrons kicked out, okay? So whenever you see the word ion in physics, it means an electron has been booted out. We'll learn more about that when we do our atomic physics unit, unit 4, okay? But ion in physics, unless you're told otherwise, it means it's positive because it has an electron kicked out. Now in chemistry, fluorine ion would always be an anion. It would be negative, okay? But gotta remember, we're dealing with different concepts and principles in chemistry than we are in physics. So it's ions are always positive unless told otherwise. How does this happen? Usually it's hit with something, okay? Often just hit with energy, like light energy, okay? Or some kind of electromagnetic radiation. So we'll just call it smashed. It's smashed and E minus are kicked out. Electrons get kicked out. That's what we mean when we say something is ionized in physics. Okay, so unless you're told otherwise, ions are always positive. So the force vector on a fluorine ion. So if I'm a little fluorine ion, F plus, okay, that's a positive charge. So ask yourself, will it feel a force in the same direction as the electric field, parallel to the electric field, or will it feel force in the opposite direction as the electric field, anti-parallel to the electric field? Okay, and remember, electric field is defined as the direction of the force that a positive charge would feel. So since we have a positive test charge, it will feel that force that way. Okay. Now, using the words parallel or perpendicular, compare the direction of the equipotential lines to the electric field vector. Okay, so the electric field vector is there, the red one. Okay, the blue one is our equipotential line. So what's the direction? How do they compare with in terms of parallel or perpendicular? Well, they're perpendicular, right? That's at a 90-degree angle. Okay, so the equipotential lines in this case are perpendicular to the field lines. That's actually true for all equipotential lines. So even when we're talking about a source charge field, okay, if I have a positive, a single source charge, let's first draw the, I'm actually going to make that a different color. Even if I draw some positive source charge that's producing an electric field, first of all, which way would the electric field be? It's going to be away because that's what a positive charge would want to do. So it would be perpendicular away from the surface of the positive charge. Okay, it kind of looks like anti-gravity, the opposite of what gravity would do if we were thinking about this as a gravitational field. Okay, but it's not, it's an electric field away from the positive charge. And as we learned yesterday, where are the equipotential lines here? Well, there's going to be one here. A point here will have the same potential difference as a point here, and a point here, and a point here, and a point here, and a point here. So essentially, the equipotential line is a circle with the same radius all the way to the source charge, right? That's actually the definition of a circle. It's a shape in which all points on its perimeter are the same distance from its center, right? So that is an equipotential line. There's another equipotential line here. And we could really draw infinitely many equipotential lines. But what I want you to notice is, remember, we said the electric field was coming perpendicular away from the surface of the positive charge. The same way when we talked about gravity, it was perpendicular in towards the surface of the Earth or whatever object it was that was causing the gravitational field. So notice, if those electric field lines are perpendicular away from that positive source charge, well, they're also perpendicular to all the equipotential lines, right? If you look at each one, it comes perpendicular to the equipotential lines. So equipotential lines are always perpendicular to electric field lines. Okay, the equipotential lines to the force vector. Well, can the force vector ever be anything other than parallel or anti-parallel to the field, to the electric field, right? Even if this were not a positive charge, if it were a negative charge, okay, if I put an electron here, what kind of force would it feel? It wouldn't feel in the same direction as the electric field, but it would feel it in the exact opposite, right? Anti-parallel, we would say, okay? And so either way, though, how does that compare to the field lines, right? It's always going to be parallel, right? That's always in the same direction. So it's always parallel, yes, or anti-parallel, but really anti-parallel is just more of a fancy version of a parallel. Okay? Anti-parallel just kind of brings direction into it. So the equipotential lines to the force vector, those will, oh, I'm sorry, I'm thinking ahead. Okay, that is our answer to 3. I just kind of explained our answer to 3, right? The electric field vector to the force vector, that's always going to be parallel. I was getting ahead of myself here. The force vector, like I said, must always be parallel to the field lines. And since the field lines are always perpendicular to the equipotential lines, right, then this will not be parallel. Sorry, this should have been our answer to 3. Okay, it's not parallel. It's definitely perpendicular. Okay, if we go back up and look at our thing, here are our equipotential lines. So again, you could have a force this way, right? All of our equipotential lines, we could draw in a bunch more. Like we said before, 100 volts would be the halfway point, right? So if I go about halfway, there's another one that's at the 100 volts, okay? But notice again, it's perpendicular to the field lines, right? And therefore perpendicular to the force vector. Whether it's going this way or this way, the equipotential lines are perpendicular to it. Okay, so some more looks here at energy changes, caused by moving within a electric field. Okay, let's just remind ourselves a little bit before we even set out to answering this. What does this mean here, right? This is the symbol for a battery, essentially, okay? And a battery, as you might know, if you've ever used one, has a negative terminal and a positive terminal, okay? So I think that of the negative terminal, that's the source of electrons, right? So, or at least where would electrons go? Think of this as a negative terminal, they would want to get away from it, right? So this plate is going to have an excess of electrons and therefore a negative charge. Where would a positive charge go from here? Well, positive charges don't move, but we can also think that negative charges would kind of leave here, be drawn towards the positive, jump across, and then want to get away over here. So all the negative electrons have left here, leaving this with a positive charge. So there we go. Now we know the charges on our plates. Okay, so really quick, I'm going to draw it outside just to not clutter things up. Actually, no, I can draw it in here. What is the direction of our electric field? Is it down or is it up? Answer that in your head. Okay, it would be up because that is what a positive charge would want to do. Okay, if I'm a negative charge, what force am I going to feel? Which direction? I'm going to feel a force down against the electric field, just because electric field is defined as what a positive charge would do, or electric field direction is defined that way. Okay, so if an alpha particle moves from C to E, what is an alpha particle again? Okay, and yes, this is on the back of your periodic table, but it always helps to kind of understand something another way, especially when we go and do radioactive decay later. It's good to know what an alpha particle actually is. Remember, that's just a helium nucleus. So helium, for the most part, most isotopes have 2 protons and 2 neutrons. So if you have 2 protons, what's your charge going to be? Well, it's going to be 2 times the charge of a proton. What's the charge of a proton? It's plus E. If you got 2 of them, it's plus 2E. So if an alpha particle moves from C to E, if we take an alpha particle, okay, and I move it from C up to E, is that going to increase, decrease, or cause no change in its potential energy? Okay, so let's think about it. If I'm an alpha particle, I'm positively charged, what do I want to do? If I'm at C already, do I want to fly up to E or do I want to pull down to A? Okay, so if I'm an alpha particle, I'm positively charged. You can think of it as I want to get towards that negative plate, or you can also think I'm positive, so I will move parallel, not anti-parallel. I'll move with the electric field. That's the Forcell field. Okay, so what does it want to do? It already wants to go to E. So you can kind of think about this. Does it have more potential energy at E? Potential energy, you can always think of as energy that is waiting to become kinetic. Okay, that's not a bad way of thinking about potential energy. It's waiting to become kinetic energy. So if I put it at E, right, if I take it from C to E, at C, it's got some kinetic energy it could gain. It would be moving pretty quick by the time it got to E. But at E, how much more energy can it gain? How much more kinetic energy can it gain? Well, none, right? It's already where it is. Turn this upside down and we've got a gravitational situation, right? If I'm at C, right, and I'm dropped to E, okay, in gravity, well, at E, I no longer have any potential energy. It's my max kinetic point, okay? So it's going to go from some potential energy to none if I'm an alpha particle. Whoops, not none. It's going to from some to none. That is a decrease. Decrease in potential. What happens to kinetic if I go from C to E? Well, in kinetic, I would gain because that's why the potential is decreasing, right? It's becoming kinetic energy. All right, what about if you move an electron from A to D? So again, ask yourself, what was an electron at A? What does it want to do? So if I'm an electron at A, okay, I can think of it 2 ways. I want to get towards that positive plate. I want to get away from that negative plate. I also, since I'm negatively charged, I would move in the opposite direction of the electric field. But if I'm at A as an electron, hey, look at that. I'm right where I want to be, really, right? I'm already at the positive plate. So do I have any potential energy? If I'm an electron just sitting at A, am I going to gain some kinetic energy if I'm allowed to move where I want to go? Am I going to speed up? Well, no, right? I'm kind of already where I want to be. I'm not going to fly up there. I'm already where I want to be. So this is looking good for it's probably going to gain some potential energy. So if I go from A to D, aha, Now I'm going to have some potential energy. At D, I would, if I was released, accelerate down to that positive plate. I would gain kinetic energy. Okay, so from A to D, I have a lot more potential energy. I have energy that's sort of lying in wait, ready to become kinetic. Think of this again in terms of gravity. If I'm a negative charge at A, or if I'm a mass at A and I move to D, do I now have potential energy? Yes, because if I was dropped, I would fall with the field, the gravitational field down. The only difference is because I'm an electric charge, the field we have to be a little more nuanced with our thinking of it. It works in two directions. Okay, but if an electron moves from A to D, it goes from having no potential to having some potential, so that's an increase. Now, what if a proton moves from F to C? So what's the charge on a proton? Well, it's the positive version of the elementary charge. So if it moves from F to C, okay. So if I'm a proton here at F, right, do I have potential energy? Yes, I want to move that way, right? I want to move with the electric field that way. Now, what if I move to C? Do I have any potential energy? I do, right? I'm going to, if I was released at C, I would gain kinetic energy that way. My energy would change from potential to kinetic until I hit that E point, like we were saying earlier. Is there any difference, though, between C and F in terms of potential energy? Would I gain any more kinetic energy if released at F than if I was released at C? Okay, take a second and look at it. Okay, I would say no change. Well, I wouldn't say that. That's the right answer, right? No change. It's no more potential energy at C than it is at F. Okay, and again, think about gravity, right? It's always helpful to come back to gravity because that's the one we kind of understand the best. We don't see this stuff as much in our everyday life, but we've all dropped stuff before, right? So if I lift something to C, right, and I drop it, it's going to go just as fast as if I lift something to C, walk over, take 10 steps to the right to F, and then drop it, right? It's going to get the same change in energy in the end. It's going to go, the potential to kinetic will always be the same. Okay, so it did ask us to justify our answer. I kind of did it out loud, but let's just wrap it up. Decrease, it's been moved against, it's been moved with, that's why it's decreased, right? It's been moved with the direction, when I just say with, I just mean in the same, I guess, with the direction E would have caused it to, or in the same direction the force it would have exerted on it. Okay, so for our B, for our electron, the same exact reasoning, really, just the opposite, right? Same reasoning, but it's moved against. Now it's moved against the field. So we've actually given it some potential energy, right? Same way, if you drop something, it's losing potential energy because it's now moving with the gravitational field. It's moving down with the gravitational field. But if you pick it up against the gravitational field and therefore against the gravitational force, you give it potential energy. Okay, now if a proton moves from F to C, we could think of it as it's moving perpendicular to the electric field. So we're not moving with it, we're not moving against it. There's really no change here, right? We're just going side to side. It has no more potential to move at C than it did at E, or at F, sorry. Okay, use the following information to answer the next question. Compare the electric fields at locations X and Y. Okay, so at locations X and Y. At X, what distance are we in terms of our separation from the plates? Well, our total, right, is going to be 7.5 centimeters. Let's just go ahead and say we are 1/3 here, and then this is the remaining 2/3. Okay, if we're 1/3 here, we have 1/3 the separation distance. What does that mean for our voltage? Well, we would have at this point, okay, at this equipotential line. By the way, sorry, just something I meant to point out. If we go back here, what are these lines? What are these dashed lines? What would be the name for those? Take a second, think about it. Okay, I'll give you a hint. What is the same at every point on those lines? The potential energy something would have, right? The potential energy or the potential it would take, the potential difference that it would take to move from that position to some other position is the same. Okay, so those are equipotential lines. Okay, which is also what I've just drawn here. That's an equipotential line, right? Uniform voltage, uniform electric field. Sorry, not uniform voltage, uniform electric field, therefore uniform force. So that is an equipotential, right? That at every point along that, the voltage is the same. But at that point, if we're 1/3 away, okay, so then here, our V, let's call it the voltage at X, because that's where point X is equal to 1/3 the total voltage, okay, which is this guy. So equals 1/3 of 400. Whoops, forgot my units. That's 133.33 repeating volts. What about at Y? Okay, well, if X is 1/3, then what distance is Y away? If we're choosing this as the direction we're going to do it in, okay, then Y is 2/3 away. It's twice as far. If 2.5 is 1/3, then 5 is 2/3. So the potential difference at Y would be 2/3 of our potential difference. So 2/3 of 400, which gives you 266.6 repeating. Okay, by the way, just because I can hear some of you now, how do we know that these are this way and not flipped around? Okay, you will get the same result if you had, say, chosen this to be kind of your 0, and then this was 2/3 away, and this was 1/3 away. You will always get the same result in the end. Okay, so as long as I'm choosing it the way, as long as I'm being consistent, as long as I don't make them both 1/3 or something, say I'm going to define this as 1/3 and then suddenly go and say I'm going to define this as 1/3, right? You kind of got to pick your 0, pick your full distance, and then say, okay, well, that's 1/3, that's 2/3, okay? Just be consistent and you get the same result either way when it comes down to it after. Okay, so let's compare the electric fields at locations X and Y. Now, this is a good question for understanding it first in terms of theory, and then if we really want, we can go and prove it mathematically. So I'm going to ask you, what's the difference between the electric field between these two parallel plates at location X and at location Y? Take a second, think about it. Okay, but we have two parallel plates. When we have parallel plates, what do we know about the electric field? Okay, so this is our positively charged plate, so we would say the electric field. This is positive because I know that's the positive terminal. So that is the direction of the electric field. Okay, which doesn't super matter for answering this question, but I guess it never hurts to have more information. Okay, how does that electric field change throughout? If this is a parallel plate, okay, if it's two parallel plates, what do we know about the electric field? It is uniform. So what's the difference at X and Y? Nothing. They're the same. Okay, compare them. Why? Because uniform electric field. Remember, the further I get away from the positive plate, if I'm a positive charge, the further I get away from the positive plate, and so the weaker its push gets, the closer I'm getting to the negative plate. And so the stronger its pull gets. So the whole way I'm always feeling a uniform force, right? Yes, this won't be pushing me strong. This plate won't be pushing me as strongly as I get further, but this plate will be pulling me stronger. So there's a give and take there in terms of the electric field, and that's why it stays uniform. And the force, therefore, stays uniform. Okay, and if you don't believe me, back it up with our equation. Electric field is equal to the potential difference over the separation distance, the distance you are at within the plates. And so remember, as we go across, the voltage drops, but so does our distance. Okay, so that electric field stays constant always. Now let's mathematically prove it. Let's mathematically check. Do we get the same answer at X as we do as Y? So with mathematically at X, okay, the electric field magnitude equals the potential difference over the separation distance. And there we have We calculated it to be 133.33 volts. And what's the separation distance? It's 2.5 centimeters, which is 0.025 meters. Okay, and that gives you 5,333.33. Repeating, the units of electric field are newtons per coulomb because volts are joules per coulomb. So when we divide by meters, we have kilogram meters squared per second squared divided by meters. That's kilogram meters per second squared per coulomb, or kilogram meters per second squared, often called a newton. Okay, let's look at Y then and see if we get the same result. So at Y, we get that the magnitude of the electric field is once again equal to the potential difference divided by the separation distance. Now at Y, it was 266.66 volts. It was repeating, divided by 0. What's our distance now? It's 0.05 meters, because it's 5 centimeters. And so we would get there that it is, you plug that in, also 5,333.33 newtons per coulomb. Okay, so they're the same, which we already knew, but feels good to prove it, doesn't it? Okay. And so again, if you had switched those, if you had said X was the 2/3 position and Y was the 1/3 position, there'd be nothing wrong with that, as long as you correctly incorporated the voltages into that. Okay, compare the accelerations of an electron and a proton at each location if we ignore their weights. Okay, ignoring their weights means ignore the force of gravity that they feel. All right, so what's an acceleration? What is every acceleration? Okay, according to Newton's second law, acceleration is equal to the net force acting on an object divided by that object's mass. Okay, so if we ignore their weights, what forces are acting on them? If I put a proton and an electron in here, and to this electric field here, what forces are acting on it if there's no weight? Well, it's just the electrostatic force, right? So it's just the electrostatic force divided by its mass. Fe is F net in this case. Okay, great, but what's Fe? Can we figure that out? Well, what do we kind of know here? We know the electric field, right? We just found it, okay? We know the charge of a proton and the charge of an electron, which is usually the relevant information when talking about fields. So let's just think, how are we going to get Fe? Okay, and again, we have the electric field, we have the charge. We could even also kind of start over here if we wanted. We have that the electric field, okay, equals Fe over Q. So Fe equals Q times E. If we hadn't just kind of done this step in part A, just because I want to show you it again because this is such a common calculation, okay, the potential difference over D. So now we could kind of take that, put it in, take that and put it in here, and we would have that the potential difference over the separation distance is equal to Fe over Q, and therefore the electrostatic force is equal to QV over D. Right, now take all that if you want, and well, not if you want, you got to take all that. That's Fe, so put it in for Fe. So just kind of popped out of my equation, went and found what's an expression for Fe I can use, and then popped it back in. By the way, if you're someone who would just like to calculate Fe here and find it, okay, by all means, go ahead, but be careful. Keep a lot of digits. Do not round early, okay? I am kind of going to encourage you to get slightly into this habit of finding expressions and then plugging in, because I know next year when you're off at university, your professors will definitely want you to do that, okay? Some physics courses I took in university, they would actually take marks off or even mark it wrong completely if you calculated more than once. What I mean by that is if any point along the way you made a calculation and you didn't just plug in all at the end. Now, I'm not going to be that hardcore, but even like I said, if you want to calculate here, keep some digits, by all means do it, but it is a good kind of skill to maybe start practicing when you're comfortable with it. So the acceleration is equal to then, if it's Fe over m, right? So let me just rewrite that. If it's Fe over m, well, Fe is just qv over d over m, okay? Which it means since it's being divided by d, it can go down here, qv over dm, okay? So let's compare it now for a proton and neutron, because I've found this expression, but I haven't actually needed to put it in any numbers yet. So let's just say for a proton, sorry, not a neutron, an electron. So let's just kind of compare here what we have. So for a proton, just in terms of qualitatively comparing it, what would be the acceleration for a proton at x? Okay, at x or at y, let's say. Well, it would be, if it's at x or it's at y, which way would its acceleration be? We said this is our positive plate. The electric field's going that way, and a proton is positive, so it'll go with the electric field. Either way, the acceleration of the proton, we would say, is going to be towards the negative plate. Okay. What about for the electron? Well, it's negative, so it would move against the field, but also even simpler than that, it doesn't want to be at the negative plate. It wants to accelerate down to the positive plate. Opposites attract. Okay, so acceleration away from, or away from negative plate, sure. In other words, towards the positive plate. Okay, so now, you can see I'm not plugging in my numbers here because I want to think about this, okay? You should get in the habit sometimes of just thinking your way through a problem, okay? What can we say without doing any numbers? What about the magnitude of the acceleration of the proton versus the magnitude of the acceleration for the electron? So what's the difference between the magnitude of the acceleration here and the magnitude of the acceleration here? Or is there a difference? Maybe there's not. Okay. What factors play into the acceleration? Let's look at our equation here. So think about what's the same between a proton and an electron here. What, if anything, is different? And so we're placing them in the same electric field. So between the same parallel plates, to be even more specific. So voltage and separation distance really aren't going to be different. Yes, they're different at x and y, but as we've already seen, right, however much the voltage changes, the distance changes. But we're just saying in general, let's compare protons and electrons. Okay. Well, what's the same? Let's start with charge. Between proton and electron, what's the same when it comes to charge? What's different when it comes to charge? Same magnitude, right? E being 1.6 times 10 to the negative 19, just opposite signs, but we've already kind of covered that with our direction. So Q is the same in magnitude, so the acceleration won't be different because of Q. However, what about M? Are those the same between a proton and an electron? Okay, and as we kind of know from Science 10 or chemistry, electrons have a much, much smaller mass than protons, right? And if you didn't remember that, it's okay because it's on the back of your formula sheet. But again, electrons have a much smaller mass than protons. So what will that mean for their accelerations? Will an electron accelerate easier, or will it be harder to accelerate an electron? Okay, and according to Newton's second law, acceleration is inversely proportional to mass. The bigger something is, the harder it is to accelerate. You know this, right? It's easier to accelerate your bike if you're pushing it along than it is to accelerate a car with a dead battery if you need to start that car, okay? So the magnitude of the acceleration will be smaller for the proton because it's got a bigger mass, okay? It's the car, it's not the bike. So the electron is the bike. It will be larger because of its mass, okay? So because smaller m, now we can only say this because the Q's are the same too, right? If the Q's were different, if the charges were different, we would have to consider that. So we'll be larger because smaller m, but same charge, okay, will be smaller because larger mass, same charge, as the electron, that is, okay? So now we've just kind of thought through it a bit, right? Never a bad exercise to just kind of think your way through it. It does ask us to compare them at each location, and I've kind of just been comparing them in general, but I want you to think, will the accelerations be different at x or at y for either the proton or the electron or both, whatever, okay? How does the acceleration change for the proton and electron at y versus for the proton and proton electron at x? What causes an acceleration? A force, right? How is the force changing between x and y? Well, I'm going to take it a step further. In an electric field, what causes the force? I kind of gave it away there. The electric field causes the force, right? The electric field, maybe not causes the force is the right word for it, but it is, the electric field is the ability for a force to kind of be applied if you are to enter that field, right? And so uniform electric field, therefore uniform force, therefore uniform acceleration. So whether you're at x or y actually makes no difference, okay? So maybe we'll add that note in here. Location x or y makes no difference because E uniform, right? Therefore, F uniform, and then what the question actually asked about, therefore, acceleration is uniform for any particle put in there. Okay, so I'll leave it to you if you want to go ahead and actually calculate the accelerations of both for the proton and the electron, but I did kind of want to just do that as more of a thinking exercise than an actual math exercise. But we have the equation, okay, so you could go ahead and plug it in there and there. You could even, if you want to do it at x and do it at y and compare your answers there. Okay, so I'm going to leave that for you as kind of an exercise. Try that out.
Okay, so here we have a diploma style question on page 21 of the notes here. Okay, and it asks us if the charge at the point A is positive Q, okay, and the charge at point B is negative 16Q. Okay, so it's take Q and multiply it by 16 and then give it the opposite charge. Okay, on the line joining the two charges, the electric field will be zero at which point? And it says that the diagram is to scale. Okay, so whenever you see this note, okay, that means you either can and usually must, okay, so not only can you, but you must, to solve it, whip out the ruler. This is like that momentum question from your 9.4 assignment / quiz, okay? So when we look here at that, I'm just going to pull out a ruler. Okay, so we're going to just see what do the distances between each point kind of look like. So I have here from point 1 to 2, I'm just kind of getting my bearings here. From point 1 to 2, we have, looks like, and this might be slightly different scale to yours, but that would be 20, so that's, right, that would be then there, 21, 2, is that 3? Yeah, so 23 millimeters, roughly. Okay, let's look at the next part. So from there, it's about 23 millimeters from A to 2. That's about 23 millimeters. So now we've confirmed with our ruler that all points are equidistant. On the line joining the two charges, the electric field will be zero at the point what? Which point? Is it at 1, 2, 3, or 4? So the line connecting the two charges, well, that's the line that connects all of these points, right? So we're asking, right, the net electric field, because we have two source charges here. So they each produce their own electric field, right? With point sources, what is the electric field? It's KQ over R squared. Okay, so at point 1, there's an electric field from A equal to KQA over RA squared, right? This separation distance. But don't forget, there's also an electric field. If A wasn't here, would there still be an electric field? It would be the electric field from B, right? It would be KQB over that R squared, that separation distance. But since they're both there at once, and electric fields are vectors, right? They're both present, and so they will add vectorially. So let's figure out first, let's just go one at a time. Let's start at point 1, okay? And we'll go until we figure out what we need. So if I'm at point 1, which way is the electric field? Split it up one at a time. If I'm at point 1, which way is the electric field at caused by A? Okay, so if I'm at point 1, electric field, remember, there's nothing here. This is a point in space. So to define direction, we have to use our convention. That electric field is always in the same direction of the force that a positive charge would feel. Okay, so if I was at 1 and I was a positive charge, which direction would be the force that I would feel? Okay, so if I'm at 1 and I'm just speaking from A, okay? From A, the force would be pushing me away, right? Like repel. So if I was a positive charge, I'd be pushed that way. So that is the direction. I'm not going to pay too much attention to magnitude right now. That's the direction of the electric field caused at point 1 by A, okay? Away. Now, let's consider what electric field would you feel at point 1 caused by point B. So again, caused by charge B, I should say. B really is a charge, right? A really is a charge. However, 1 is just a point in space. We're just looking at the electric field there that's present, whether or not we have a charge there. But if I was a positive test charge at point 1, and this is negative, okay, I'm going to feel an electric field towards it, right? If I'm a positive test charge, I'm going to feel a force towards it, and so that's the direction of the electric field caused by B. Okay, so I kind of drew this one about roughly the same size. Why did I do that? Well, this one is positive, right? But it's really close. Positive 1Q, but it's pretty close. Okay, so this electric field might be fairly strong because of the distance. This one is, yes, very far away, but it's negative 16Q, so it's 16 times the magnitude of charge. So I kind of said, let's do a balancing act there. Now, let's kind of do the math here. Let's think about it. Okay, so let's compare some magnitudes here. Let's first think about it just in terms of R. Okay, so I'm going to, let's use this color here. R from 1 to A, right, is that. R, let's call it 1 to A. And then we have R from 1 to B, right? R from 1 to B. How can we compare R1 to B to R1 to A? Well, R1 to B is 1, 2, 3, 4 times as large as R1 to A, right? So RIB equals 4 R from 1 to A. So what would that mean for the forces if the charges were the same? Okay, for the electric fields, if the charges were the same. Okay, well, we would say that the electric field at A equals KQ if the charges were the same. So let's just say KQ over R1A squared. Now, electric field at B equals KQ. We're just going to pretend, what if the charges were the same? Okay, over RI, or 1B squared. Okay, but we just said R1B squared is 4 times 1A squared. 4 times the separation distance. So KQ over 4 RIA squared. Okay, now that 4 gets squared. Part of that gets squared. So we have, that's KQ over 16 times the separation distance between, 1A squared, right? I'm just replacing, since the separation distance from 1 to B is 4 times 1 to A, I replace it there, and then I say, okay, 16. Now hang on, that means that the electric field at B, what is this part right here? What is just this piece? KQ over the separation distance from point 1 to A squared. Hang on, that's just the electric field at A. So in other words, the electric field at B is equal to the electric field at A divided by 16, or electric field at B then therefore equals 1/16 the electric field at A. Okay, if charges were the same. So this is just looking at it based on the separation distance. But the charges are not the same, right? The charges are not the same. The magnitude of the charge at B is actually 16 times greater. So what would I do to compare? I would put a 16 in there. And then what would happen? I'd have 16 times 16, right? 16 times 1 over 16. So, and really, sorry, I should be having these in everywhere. Okay, these should be everywhere because we already know they're not in the same direction, right? They're in the opposite direction because the charges on A and the charge on B are opposites. So if the charges were the same, and again, magnitude. Charges were the same magnitude. So let's take a look then. If I were to say, yes, if only the radius was different, we would have 1/16 the electric field strength at A than we do caused by B at point 1, right? But we have 16 times the magnitude. So basically I would multiply that by 16. I would replace Q with 16QA, and lo and behold, we would have that the electric field at B is actually, the magnitude anyway, is equal to the electric field at A. Now, since they're in opposite directions, yeah, I've actually drawn this pretty well. They're about going to have the same magnitudes. If I draw VAD, okay, equal magnitudes, opposite directions, so that overall what ends up happening, they cancel out. And what is our electric field at point 1 net? It's 0. So there we go. On our first try, we got the answer. Okay, it's A, it's at 1. Now, a little bit of a test smartness tool here, okay? Yes, all these calculations are great, and you can think about it and check your work if you've got lots of time, but let's just be test smart here for a sec. At point 1, okay, it's possible for the electric fields to be opposed, right? EB could be away from EA because at A will be pushing to the left and B will be pushing to the right. But let's look at point 2, and for that matter, point 3, and for that matter, point 4. Okay. So if I'm at point 2, okay, let's just think here without breaking into calculations. Actually, sorry, for point 2 and 3, this is going to be true. For point 2, okay, I'm a positive charge. Which way is the electric field caused by A? If I'm a positive charge, what force would I feel? I would feel the force that way, and so that would be the electric field caused at A. Now, what would be caused by B? What electric field would I feel? What electric direction would I feel if I was positive? Well, I want to get towards that negative, right? So, hey, EB would also be that way. Now, I'm really not paying attention to magnitudes here. We're just focusing on directions. So, if the electric field caused by A and the electric field caused by B are in the same direction at point 2, how could they ever add vectorially, right? How could they ever add to give us 0? They're in the same direction. They're helping each other, right? So 2 right away, when I'm looking at this as a student, no way, right? How could 2 ever be the answer? And for the same reason at 3, right? Yes, it'll be slightly smaller, but the electric field at A will be that way, right? The electric field caused by A, sorry, will still be that way. It'll be repulsive. The force would be, okay, if you're a positive charge. And yes, it'll be slightly stronger because you're closer to B, but again, it'll be in the same direction. So same idea at 3. How could those ever add to give you 0? They're in the same direction. They're helping each other. So right away, boom, we're going to eliminate C, okay? And then at 4, yes, you would kind of have to maybe pull out a little bit of math, but realistically, you can probably look at that and realize, hang on, okay? So sure, at point 4, right, the electric field caused by A is still that way. It's pretty weak now because we're pretty far away. The electric field caused by B, yes, is fairly strong that way, right? And yes, they're in opposite directions, so there's, in theory, it's at least possible for them to maybe add to give us 0. But I mean, come on, right? 16 times the charge and you're only that far away, that's going to be a very strong field. In fact, I should draw it way bigger, right? In fact, yeah, we've got a factor of 16 that it's increased because of the R, and then another factor of 16 that is increased by the charge. So 16 squared greater from B. So this isn't even drawn close to proportion. And then this tiny charge of plus Q this far away, that electric field is going to be way smaller. Okay, so is it always necessary to break out and actually calculate? No, I mean it helps to solidify our understanding, but again, use your noodle, right? Think about it. Okay, 1, 2, 3, 4. It's pretty apparent just by spending a few minutes wrestling with it that 1 is the only place you could end up with the electric field vectors canceling each other out.